So our next speaker is Thomas Jerkovits, and he's here with us in person. That's great. And this is going to work with felicitas and with Hannes Bartz on decoding hardware interleaved summary and Skew-Metric codes.
Okay, yeah. Thank you, Eduardo, for the introduction. So I don't have to say too much about the first slide here. So I just jump directly to the outline. It's just standard structure. First, I give an introduction and preliminaries. Then I will talk about the proposed algorithm, and finally some conclusion. So let's jump into the introduction. So I think the first 2 points are kind of clear. So we know already that code-based crypto is a suitable candidate for being quantum resistant. And in this talk, I will elaborate on higher order interleaved sum-metric codes of decoding them. So in the previous talk today, we already heard about interleaved codes. And yesterday we had some motivation about sum-rank metric codes for code-based crypto. And so in the previous talk, there was already the case that when you have high order interleaving, so the interleaving order is larger than the error, then there was the reference to Metzner-Kaptorovsky's decoder, and that was introduced for the Hamming metric, but was also already by Renner, Buchinger, and Bachnetze already adapted to the rank metric. And today we further adapt this algorithm to the sum rank metric and show that this works as well with kind of the same complexity. Okay, so first some ingredients. Of course, first the sum rank metric, so let X be a vector over FQM of length n. And this vector we can then partition according to a length partition into blocks. And for each block, we can define the rank, which we define to column-wise expand this block over FQ. So we get a matrix over FQ, and from this we know the FQ rank, and that's the rank of this block. And then just the sum over all the ranks of these blocks is the sum rank wave. And from the sum rank wave, we can then induce a sum rank distance over which our codes are defined in this metric. And then we have 2 special cases. If the number of blocks is 1, then we just get the rank metric, so we just have 1 block. And if the number of blocks is equal to the code length, n, then we have the Hamming metric. Okay, so the next ingredient we need is the definition of interleaved codes. So to say S interleaved code is just the direct sum of S codes of the same length. And then we can say if all codes are equal, we call them homogeneous. And if they are different, then we call them heterogeneous. And in our talk, we consider vertically homogeneous interleaved sum rank metric codes. So a special case. So that is when we have a given sum rank metric code with a length partition and the dimension k and minimum distance d over FQM and a parity check matrix, which we will need later. Then the homogeneous S interleaved code is defined by the set where we basically stack the code words, which are from the component code from before in a matrix that is S times n. And the resulting code, of course, still has minimum sum rank distance d. Okay, so the next ingredient we need is the channel model that we consider. So let's assume again a code word from an S interleaved sum rank metric code. Then we transmit this code word over a channel, which is additive plus an error matrix. This error matrix can also be considered partitioned into blocks, where each block has rank T sub I. So the ith block has T sub I. And then, of course, the sum rank weight of this error is T. So the sum over these Ti's equals T. And we can also consider the decomposition of such an error, which is not necessarily unique, in a product of 2 matrices, A times B, where the left matrix A is over FQM, and the right matrix is over FQ, and is a block diagonal matrix where each of these blocks has size T sub I, so the rank of the block times the length of the block N sub I. Okay, so this is all we need for now. And I start with the main result to formalize what our decoder does. So all the assumptions we need. So first of all, we have an S-interleaved homogeneous sum-rank metric code over FQM. We have a sum-rank channel as described before. And then if the sum-rank weight of the error is t smaller or equal than the minimum distance minus 2, and we have the full rank condition, that means that the FQM rank of the error matrix is equal to t, we can successfully decode using the proposed algorithm that I will show it just in a moment. And also note that the FQM rank full condition implies also that the interleaving order is high. So as I already mentioned in the previous talk, that interleaving order S must be larger than the error radical. And the complexity of the proposed algorithm is soft O, which means we neglect the logarithmic factors of the maximum of the interleaving order times the code length squared, or the code length cubed times m operations in FQ. Okay, and a lemma we need for describing the algorithm is the erasure decoding lemma here that says if you have an error decomposed as two matrices A times B, as described before, and the sum rank weight T is smaller than D, so the minimum distance, then assume we already know B, we can actually compute A from the syndrome matrix. So syndrome matrix is just parity check matrix times the error transposed, and then we just have to solve the linear system of equations given on the slide here below. Yeah, and this follows directly from the paper by Puchinger and Renner and Johann Rosenkilde, which is about generic decoding in the sum-rank metric. So you can find the proof of this lemma there. Okay, so how does the algorithm work now? So all starts with computing the syndrome. So we compute the syndrome matrix, which is parity check matrix times the received code word. That is equal to parity check matrix times the error matrix transposed. And then we compute the row echelon form of this syndrome matrix. So we compute a matrix P, which describes the row operations that are needed to transform P times S in a matrix such that we have all zero matrix in the n minus k minus t last rows. And this is exactly for n minus t if we have the full rank condition. If we don't have the full rank condition, then it's at least this many zeros. And on the right side, we can have then also split the P times H matrix in an upper block and a lower block. And the lower block that corresponds to the zeros in P times S, we call H sub. And this matrix we need now to proceed with this H sub. Okay. So with our length partition, we can then also slice H sub into these blocks. And another theorem then says if we have the error also with the length partitions, some rank weight T and full rank condition given, that then the row space over FQ of the error is equal to the kernel of, so each block of the error, the FQ row space is equal to the kernel of the H sub block expanded over FQ, so column wise. And the proof of this theorem follows similar techniques as in the paper that is about the adaptation of the Metzner-Kaptowski decoder for the rank weight, but with a few adaptations, of course. Okay, so with this theorem, we can basically do now the following. We can, knowing the H sub I blocks, independently for every block, we can recover the error block of the ith error block of the B matrix by just solving another system of linear equations, so the right kernel of extension of H sub I. And then we can build up the whole block, which is just the block diagonal matrix of these B blocks. And what then remains is just erasure decoding using lemma 1 to recover A. Then we have the complete error matrix, which we can then subtract from the transmitted code word and recover the code word. So kind of simple. And to summarize, I just put everything in pseudocode here. I will not go over this again because it's just the same what I already described in a bit more detail, but just to show you that the algorithm is actually very simple and very short and can be quickly implemented. Okay, now I want to illustrate a bit more the difference of the algorithm working for Hamming metric, rank metric, and then for some rank metric. So let's consider first the special case of the Hamming metric, where we have now the error. Let's assume we have three errors, so at these 3 positions. And then this can be decomposed as A times B, where A is a matrix over FQM, and B is a matrix over FQ, and it has a special form that we have the unit vectors at the positions of the errors. Right, and then if we would proceed with our algorithm and extract H sub, so the n minus k minus t last columns of the H matrix after we bring the syndrome matrix into row echelon form and multiply with this P matrix from the left, we get H sub. And then it's exactly 0 at the error positions. So all 0 columns at the error positions. And this already gives us the error positions, which just remains to do erasure decoding for Hamming metric codes. So we already done basically. And then for the rank metric, it looks a bit different. So we don't really have error positions that I can visualize. Then the same holds for the decomposition. We have a matrix A over FQM and B over FQ. And we can compute H sub. And then we get a general form where we can extend each row. So each block here, which is then a generating set of the row space of the first block here. And the union of these row spaces, we can then compute this B matrix. And then again, also with this lemma 1, we can recover A. And now combining these two basically leads us to the sum rank metric case. So we have, again, kind of error positions because we can have blocks where no rank errors appear. But now in the general case, this is not like in the Hamming metric case, we have here the possibility of having a wave that's corresponding to the FQ rank of this block, which is T sub I. And the decomposition looks also more general. So on the B side, we don't have unit vectors anymore, but we can have blocks that size corresponds to the length partition and the partition of the error waves. And same, we can compute H sub, which also looks more general then. But now we have, as for the rank case, for each block, we can now independently recover these blocks of the B matrix. So these T sub I times Ni. And then, so when we have built up the whole block B with the block diagonal matrix structure, we can recover A. Okay. And yeah, this already leads me to the conclusion. So we proposed a Metzner-Kapdorowski-like decoder that allows correcting some rank errors with weight up to D minus 2 if the full rank and high order condition is fulfilled. And the proposed decoder can be used for determining the security level of code-based crypto systems. So the message will be that large interleaving order is bad. So as already in the previous talk was said that the more interesting case is for smaller interleaving order, since because of the existence of such algorithms, and also because you have the trade-off. Okay, and yeah, what I want to point out here is very important that this algorithm works for any code. So you don't need to have any structure for the component codes. You need to have the interleaving structure, of course, but the component code can be completely unstructured, and you still can use this algorithm with the proposed complexity and can decode these errors. So you just need to have the full rank condition. And the last point is why the talk is called also Decoding of High Order Interleaved Skew-Metric Codes. And this is simply because you can use an isometry explained in the paper by Martinez-Penache that gives just a transformation of the skew metric into the sum rank metric and vice versa. So you can transform the skew metric codes into the sum rank metric code, use our algorithm, and then transform it back. Okay. Yeah, that's it already for my talk. Thank you for your attention, and looking for your audio questions.
Stop your questions from okay, so I have a very simple question.
Yeah.
It's what you see as the next steps now. Action. For example,
So you mean to extend this algorithm? Yeah, so there might be some, I mean, the restriction of having the full rank condition is maybe very strong. So we want to look also to be able to decode, so maybe not with the same complexity, with an increased complexity that might be not even polynomial, but to look at if you can improve or use some techniques from this algorithm also for if the full rank condition is not fulfilled. Then also to analyze actually how high is the probability of such errors to appear. So if you don't use the full rank condition, so you just draw some rank errors at random, and how high is the probability that this full rank condition is fulfilled. This is also still open. And yeah, so for the Hamming metric, there's actually a paper by Ronnie Roth about the issue when you don't have the full rank condition fulfilled. So because for the rank and Hamming metric version of this algorithm, you also have this full rank condition. But we understood that you don't really asymptotically gain anything by, so with comparing it to a naive approach. So that, yeah, maybe we can use some ideas from there. Yeah.
Also something simple, in comparison to the versions for rank and for Hamming, is there efficiency difference in the decoding for some? It's easy to implement.
Yes, so I mean the algorithm itself is very similar to the rank metric case and the Hamming metric case. It's basically just a generalization. So you can use the algorithm also for the rank metric, and the Hamming metric, it just falls out for this kind of algorithm that we proposed, and the complexity are all the same for all three versions. So you don't gain anything, but you also don't lose. If you compare with the total code length. Yeah.
Let's thank Thomas again.